Okay, here's an interesting problem regarding some polymers. We've got a mixture of plastic beads consisting of polypropylene, or PP, and polyvinyl chloride, PVC, in a 1 liter beaker containing distilled water. After stirring the contents, the student observes that the beads of one type sink to the bottom and the beads of the other type float on the water. Here are the structures. So the first thing we're asked, given that the spacing between polymer chains in PP and PVC is similar, the beads that sink are made of which polymer? So see here how we've got CH2, CH3, CH2, CH3. So this is why we put parentheses over here with an N, because we're saying that's the repeating unit. So that little segment right there is going again, 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 all the way down for thousands and thousands or millions of atoms. Over here, it's the same, except that instead of this methyl group right here, we've got a chlorine atom. So the question is, which one sinks, which one floats? So what is it that determines whether something sinks or floats in water? So that would be density, and density is mass per unit volume. So given that the spacing is similar, the reason they're saying that spacing is similar is that we're not going to really look at volume, right? Structurally, they're very similar, but they differ in mass, right? This is heavier. Chlorine is heavier than a methyl group, right? Chlorine is quite a bit more. The methyl is only 15, right? So this is quite a bit heavier. So that makes the polymer much heavier overall. And so PVC is going to be the one that sinks, right? Heavier in the same amount of volume. That's a greater density. So that is going to be the one that sinks. So PP is synthesized from propene, and PVC is synthesized from vinyl chloride. The boiling point of this one is 226. And that is lower than the boiling point of liquid vinyl chloride. 260 would be that one. Account for this difference in terms of the types and strengths of intermolecular forces present in each liquid. So what we want to understand is that what are these doing? So every molecule can do dispersion interactions, right? So over here, dispersion, and over here is dispersion. But what we also need to understand is that whereas there's not really any dipole moment here because we don't have any polar bonds, but over here a carbon-chlorine bond is polar, right? So we have this bond dipole right here, which means that this is capable of dipole-dipole interactions, right? Any molecule that has a net dipole can do dipole-dipole interactions, right? They can interact with one another. Furthermore, this one makes stronger dispersion interactions, and this one makes weaker dispersion interactions because the chlorine atom is bigger, so we're talking about a slightly larger electron cloud, right? This chlorine atom, chlorine is one period down. It's got an additional shell from carbon, so this is a little bit smaller. So we're talking about the larger electron cloud is more polarizable, which results in stronger dispersion interactions. But probably more significantly is the potential for dipole-dipole interactions. We have a bond dipole, therefore we have one polar bond, therefore we must have a net dipole. And these dipoles can interact with one another. So there's that, not to mention the fact that this is more massive. So they tend not to care too much about mass with these questions, but it is important to understand that there's more mass here, and more mass means something will boil higher. So that's a factor just to remember as well. So, but they want to talk about intermolecular forces, so that would be those two. Weaker dispersion, stronger dispersion, and dipole-dipole. So we got one more little thing here. The student measures the enthalpies of combustion of propene and vinyl chloride. So with 2 moles of vinyl chloride, Now this is undergoing combustion, so here's the balanced chemical reaction for the balanced equation for the combustion, and this is going to release 2,300 kilojoules per mole. So that was measured. Now, using the table of standard enthalpies of formation, we want to determine whether the combustion of 2 moles of propene, so the other subunit to get the other polymer, would release more, less, or the same amount of energy that 2 moles of vinyl chloride releases. So here's that balanced equation. We have to do a calculation here. We have to use these enthalpies of formation. So let's go ahead and do it. So when we're calculating delta H, remember there are these different ways that we can calculate delta H. We can use Hess's law. We can do a bunch of things, but one of them is standard enthalpy of formation. And all we're going to do is add up the enthalpies of formation of the products multiplied by their stoichiometric coefficients, and subtract from that the enthalpies of formation of the reactants multiplied by their stoichiometric coefficients. So what we're saying is that delta H is going to be equal to, and let's use brackets. Let's separate the products and reactants very clearly there. So 6 times the CO2, right? We're looking at CO2 because we're going products first. That's negative 394. And then we add to that 6 times for H2O, we've got negative 242. So there's our product. Now we're going to subtract from that. Now we have on the reactant side 2, and then the propene. Make sure to use this one and not this one. This is the vinyl chloride, right? We want propene right there, 2 times 21 plus 9, and then obviously enthalpy of formation for any pure element. Any element like O2 is going to be 0. So, but just, we want to put the full calculation there. So we put that all in the calculator, and we get negative 3858 kilojoules per mole. So that's the delta H for this combustion. Now let's compare that to the first one, negative 2300. So very clearly, this other one releases more. Negative 3858. That's more. That's releasing more energy per mole than the other one. So that was an interesting problem. We started out with some polymers, and then we looked at the subunits, and we talked about boiling point and combustion and enthalpy of combustion.